So last class we did vector equation for B bar, which is a magnetic field or magnetic flux density at a point P on the axis of a circular current loop or the current carrying circular loop. So it is, we said only in the x direction it will be there, in other two directions it gets cancelled off. Okay. So the expression, this is at a point P, which is x distance from the center of the loop. That's what it is. So the magnetic field that is the center of the loop itself. We have a loop, then at the center of the loop, x equal to 0 at the center of the loop. If you remember the picture, what we have drawn was some loop like that, and there is a point P, and we said this is the distance, this is the radius, this is the distance r, right? That's not radius r, that's the distance r, this is the radius r, and this is the x. So if x equal to 0, that means the substitute x equal to 0 is that you will get mu naught I r square. You have r cube down there, so you get r, and P is the I bar, and cap is the direction. So this is a vector form. Finally, every time we need to know where is the I cap, because in the previous case we assumed how the electric field is there. That's how we got this expression. That's fine. So in general, there is, in order to find the direction of the magnetic field, so in order to find the direction of the magnetic field, we have a rule called right hand thumb rule. So this is the loop we are assuming. This is the loop, whatever we have drawn here, right? This is the loop. So this is the loop like that. Center is the hollow. So if the current is going in this direction, in this loop, then inside to this hollow, there is a magnetic field in this region. It will be directed this way, going bottom to top. Okay, that means north pole will be here and the south pole will be here. So this is called the right hand thumb rule. That's why I just try to draw a right hand. So the thumb would be pointing towards the direction of the current, and vice versa also. That means if the magnetic field lines are going like this, somewhere the magnetic field lines are going this way, right? And if there is a wire inside, then the current will be in that direction, which will be the high, and this will be like that. Okay? Okay. So that's what he mentions here. Curl, that means you hold your, with your right hand, curl the palm of your right hand around the circle wire, with the fingers pointing in the direction of the current. So if the fingers are pointing towards, that's what these fingers, right? These are the direction of the current. Then upward thumb will show the direction of the magnetic field. So this is called the right hand thumb rule. Okay. So the upper side of the loop may be thought of as the north pole, and the lower side of the south pole of the magnet. This is what I have written. Here, the upper side is considered the north pole. This is the reverse pole. I put it. So let me read over actually. I will explain that part also. This is the south pole and this is north pole because a magnet is kind of virtually present there. Inside the magnet, see, inside the magnet, the lines will go from south to north inside. When it comes outside, they go from north to south. Okay, that's the reason we assume that as an upper north, below south. Okay, so the next one is, so I'm referring to the textbook, that's why I'm just putting all these things here. So remember we have done in previous episode, right? This one is much similar. There also Gauss is the total charge enclosed inside the Gaussian surface, things like that we learned. So this Ampere's circular law is another method to find out the magnetic field density. Okay, so this is another way of finding out, and this involves higher level mathematics. That's why they don't give any derivation or any such thing, but just they state that you have, for example, any wire. You have a long wire, some long wire is there. It's a cylindrical wire or whatever. Then you cut some part of it, okay, and after cutting it, you are taking a surface. That means you cut that and then you are seeing something like that, a cylinder like that here after cutting it. So, if you know the current going in this conductor is this way, so it still goes this way, current is going in that direction, then have an imaginary loop like that, a circular loop, anywhere in the cross section. Okay? And if the current direction is this way, the magnetic field will be here, arrow shown, right? That is how the magnetic field will be along that curve. That's how the magnetic field will be. So this is what the Ampere stated, saying if you do the integral, it's called a line integral, of the magnetic field density, you have small elements here. For all the set of elements you make it, then it was this is equivalent to, we used to have sigma. Sigma, this is also called sigma. Sigma indicates always totaling. You are totaling something. So, you are now looking for all the dl, not only one dl part, all the dl around that current loop. Okay, this is called Ampere's law. So, what we have Ampere's law says that this integral is equal to mu naught times of the total current passing through the surface. So this law has to be taken this way only with the picture. We say that integral of B dot dl equal to mu naught times of I, or even if you just write this entire thing as a 1 mark question, Ampere's law. Okay, this is the Ampere's law. So why he is giving that? So once you have the integration value and then you make B as a subject, you will get B is equal to something. That's what we will be talking in the next part. So the integral is taken over the closely coinciding with the boundary C of the surface. This is the boundary. Okay? So let's suppose we have again how do I apply this Amperean loop and my right hand loop. It's the same thing. That's what he says. Let the fingers of the right hand curl in the sense the boundary is traversed in the loop integral. See here the boundary is going like this. That's what the boundary going in the clockwise direction. So you curl the fingers like that with the right hand. Okay? So you imagine now you are using the right hand and you are putting, that means when I hold my hand, the fingers will be going upward. Palm is down, okay? So that's how it's going from bottom to top. That's the direction of magnetic field. Then the current will be going through that. This will be the current going through that. This is the current. That is what. So, this is the alternative way of getting the magnetic field density. And we have applied right hand thumb rule. The right hand thumb rule is nothing but, so you hold something with the right hand, the thumb indicates the direction of the magnetic field or the current. Now we get this part. Now we are trying to get the same expression what we got to the delta law for the circular loop of radius r. Now when I do the entire integral, so whenever we do the line integral like that, so this is the circular loop. That means you are actually adding all the bits of here like that. You are adding each one here. So this is nothing but, you get the circumference, like last time, circumference of the loop. So, we don't have the radius here, but then circumference is nothing but when you open, this entire thing is open, then that is nothing but the total length of the coil or loop. Yes. So that's why he says BL equal to mu naught into IE. So let IE be the current enclosed by the loop. See, these enclosed words have come even in the Gauss theorem also. So, when there is a system with a symmetry such as a straight infinite current carrying conductor, current carrying wire. When they say infinite, see, we need to understand actually why we are studying all these things. The people who complete the PUC, of course, some of them do the engineering, and some of those engineering people will be into the electrical field and electronics field. In the electrical engineering, entire thing is about the current and then sending it through so many transmission wires, right? You see huge towers, and then on that you have got the wires running from different places to different places. So the length may go from kilometers, tens of kilometers, hundreds of kilometers. And therefore, in order to understand those things at the higher classes, so we are having this as a fundamental thing. So straight infinite current carrying conductor. The Ampere's law enables easy evaluation of the magnetic field, much the same way as the Gauss law helps in determination of the electric field. It's a comparison. You don't have to write it also. Okay. So that is why, since it's the length, and length is nothing but a circumference 2 pi r, so he replaces L with a B into 2 pi r equal to mu naught I. So from that, B is equal to mu naught I by 2 pi r. This is the same result for the using Bayes-Sauer's law. Using Bayes-Sauer's law, we got the same thing. Right? That's all is the Ampere's circuit law. Ampere's circuit law or Ampere's law. Any questions on that? No. Now, each of these interesting points are the 1 mark, 2 mark questions. That's why we will have to go through. So, what it is implying? It implies that means this entire expression what is what? The field at every point on a circle of radius r. So, you are taking different points. Any point here or here, so P1, P2, P3, like that, is the same. The field is same in magnitude. In other words, the magnetic field possesses what is called a cylindrical symmetry. Cylindrical symmetry means you have a cylinder. So, if you are saying that there is a point here, and there is a point here, 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 there is a point here. So, if you have drawn this circle like that, the field here is same as the field here, the field same as field here. That means it is defining one surface, the curved surface of the cylinder. That's what it is called a cylindrical symmetry, and you don't expect any question on the cylindrical symmetry because it is written italics. Don't worry about that. So the field that normally can depend on 3 coordinates now depends only on 1. That is 1 coordinate, which is r. So whenever there is a symmetry, that's how the solutions become very, very simple. Okay. So what is it trying to say? 3 coordinates mean you always have these things like x, y, z, right? So irrespective of that, because I am not putting that any ix or iy, so it only depends on the radius r. That's what is the entire thing. What is this r actually? So he says with the wire along the axis. Okay. So every point on a circle of radius r. Okay. This r is not to be confused with the capital R what we got last time. Okay. This r is this. Okay. Why? Because we are using this for the circumference given by the. The second point, the field direction at any point on the circle, let us suppose you are trying to say here, what is the field direction? So you draw a tangent at that point, it's not exactly a tangent, so you draw a tangent, okay, and along the tangent you will have the field. So the lines of constant magnitude of magnetic field form a concentric circle. So Notice now the iron filings from the concentric circle. See, these are the things. Okay, this is there in the first part of your chapter. Okay, so here the magnetic field due to a straight long current carrying wire. In this case, the current is coming out of the paper. In this case, the current is going into the paper. So the wire is perpendicular to the plane of the paper. Ring of compass needle. The compass needle, N indicates north. That's why I have written this here, drawn this here. The other one is the south. This is also notation, compass notation. So ring of compass needle surrounds the wire. That means we have put that compass at many places. The orientation of the needles is shown. The current emerges out of the plane of the paper. In the second case, the current moves into the plane of the paper. See, if you put the iron filings instead of this compass, the arrangement of the iron filings around the wire. So, if you have the wire going like this, if you put the iron filings around, they will be like that aligned. Okay? So, the darkened ends of the needle represents the north pole. The effect of Earth's magnetism is neglected. That means the assume that this is not there. Third point. Even though the wire is infinite, the field due to it at a non-zero distance is not infinite. So B is never infinite. The field is directly proportional to the current and inversely proportional to the distance from the infinitely long current source. This is important. Okay? So you have to remember always that transmission wire I said, right? So if you really go somewhere, like you have a third floor or fifth floor or sixth floor, your house is there, you are an apartment, and then the huge transmission line just goes by side of your apartment. Okay, you can probably hear some sound sometimes, and definitely there is a magnetic field. You can feel it from the place where you are standing, how far you are from that wire. Okay, so that's what he explained in the third point. Fourth point. There exists a simple rule, that is about the direction. It is called a right hand thumb rule. Grasp the wire in your right hand with your, we have covered this already. Okay? So this result is basically same as what we got the Biot-Savart law. So this we have, up to that we have covered. Okay? So the next part, what is given there, we can go to the textbook, page number 151. So you have that. So we'll be talking something about what we already know. So in the 10th standard, we studied about the solenoid. We'll be talking about the solenoid, and there is a small expression to be obtained, and then we'll be talking about the toroid. Okay. So these two will be covered now. After solenoid is important, there's a lot of practical applications. Then we will talk about how the current going through two conductors, parallel conductors, and then the corresponding magnetic field. After that, we will see the torque on a current loop. That means if we keep this current loop in a magnetic field, how it moves or rotates. Torque means circular force. Okay? So these are the things we'll be talking about. So how do we get into solenoid? We just talked about one loop, both with Biot-Savart's law or with Ampere's equivalent law. We just looked at one loop, or even we can call it as a one turn, only one turn. So, let's suppose you have this like a string, like that. You got it, right? So this is like a many turns of coil. So the turns can be n number of turns or whatever. So for one turn, we know how to calculate the magnetic field at the center, or whichever way. Let us suppose we put the direction, if this is the current direction, So this loop is nothing but this first loop up to this point. Okay? Then you are again repeating another loop like that. So if this is the current, so now put the thumb in the direction of the current. So all the four fingers, right, they will be coming like that. They will be curling like this. Okay? So that's why in the picture if you see, so you will have the magnetic field direction will be going like this, right, obviously. So the magnetic field lines will be going along this line. So it's the air. Inside nothing is filled. We have got air inside that. Okay? So the magnetic field this way, that means you will have the remaining lines of magnetic field everywhere if you consider. And you going this way, and then you have like that. So since it is going this way, we consider this side will be the south pole and this side will be the north pole. You can actually keep it vertical also. You don't have to be horizontally. Okay? So this is what we call actually a long solenoid. We mean that solenoid length is large when compared to radius. This is a very common thing. So when we say something with wire is a long wire, so this is the radius. So this radius is so small when compared to this entire length. So in this case also, a solenoid is nothing but like this, a coil whose radius is very, very small. See? It consists of a long wire wound in the form of a helix. I told in the last class, right? Helix means the radius is same for all the turns. The neighboring turns are closely spaced. Only for our purpose to see that they are like a coil, we put them this distance here. Otherwise, this distance is very, very small, very closely packed. Okay, so the turns are many turns per 1 centimeter. So each turn can be regarded as a circular loop. The net magnetic field is the vector sum of the field due to all turns. So one turn we have seen. Previously we have seen for one turn. Let me erase this first. Let's come to this later. So for one turn we got V bar equal to that mu naught by 2 R into I naught or whatever, right? So this is what we got. This is for one turn. So if you want for all the turns, then you have to get the net magnetic field, which is nothing but the vector sum of all of it. So in general, all these wires, they are enameled. Enameled wires are used for winding so that the turns are insulated from each other. You can't have both the wires touching each other. They are close, but they are not touching. So there is a small insulation between these things. So you have a small, very closely wound. Okay? So like that. Now we will be finding out what is the expression for the magnetic field in case of a solenoid and how is its direction. Which direction is being moved. Okay? And he uses the Ampere circular law, Ampere's loop he will be considering, and from there he will actually get the expression. Generally, it is asked, in such a way that you describe the solenoid and then write the expression or just get the expression. See? So now if you look at it in the picture, he just draw figure 4.18. All the dots and the crosses you see on the top and bottom, dots indicating that the current is coming through that. Cross means current is going into that. Current is going into the paper, and let me draw it so that you can have better picture. So if you see there, he has put so many dots here. This is basically, this dot is this part. Okay. So he is not showing the wire. The wire is taken out, but we are assuming that this is how. So the current is actually coming out of that, like that, in this case. Okay. So it's wound like that. The current is going and then entering like this. So you have a cross here, and then the corresponding cross here, into, like this. So this is for the derivation purpose. He assumes that this is how it looks like. For each dot I have a into kept here. Okay. So this figure, whatever you have, which is 4.18. Okay. So that's the picture we are seeing there. The field at the exterior point Q, if you are taking the exterior point Q, is weak and is along the axis of the solenoid with no perpendicular, no normal component. That means you have a point Q somewhere here or somewhere here. At these places, the B bar is weak. So we are trying to find out at a point P inside, some point P inside. So consider a point P inside. The field outside the solenoid of course is 0. We shall assume that the field outside is 0. The field inside becomes everywhere parallel to the axis. So as we know, right, we said this is the current direction. That means it is coming like, the fingers are actually facing us, coming out of the page, and that's why the magnetic field will be along this. The magnetic field will be along this. So this is the magnetic field direction. Okay, so which everywhere parallel to the axis. If you want some more, then we will have like that. This is the magnetic field direction, B bar. So you see on the right side he has put the thumb and then the right hand thumb and all the stuff. Correct? Next page, 152. He talks about consider a rectangular Amperian loop ABCD. Do you see some picture? It shows that AB like this. I am drawing with a arrow here. So you have to get a little outside this point. You have like that. This is A, B, C, D. So considering the Amperian loop, so ABCD is Amperian loop. Just like that Gaussian surface, this is imaginary. It doesn't exist like ABCD or whatever. Okay? We are assuming this shape for a good reason also. We'll come to that. So along CD, that means if you are looking at this, in this loop, the field is 0 because we said already outside at depth B is weak or 0. We assume it is 0. So along CD, it is 0. Along transverse sections BC and AD, these are the transverse verticals BC and AD. Okay, the field component is 0. Why? Because this and this, right? They are perpendicular to B. This is your BC and this is your AD. This is perpendicular, right? And therefore, so thus the two sections make no continuation. Let the field along AB. Now what is remaining? Only AB. So the field along AB is B. That's what we are considering and we want to find out that as a B. Okay? So that means out of all these things, we only need to know about the length of the amperian loop. This is the length of the amperian loop. This is AB. This is the length of amperian loop. This is the effective length. Because all of the part it is 0. We don't need to bother about it. Fine. Then, if there are n number of turns per unit length, we had already given the expression that B is equal to, we already got B into L equal to mu naught I. This is as per the ampere circuit law. So B L is equal to mu naught I. So in this case, if you are assuming that this L is equal to H, for example, if AB, that AB length is equal to H. So we are only considering along this we may have many terms in the limit. Understood, right? Therefore, if I am assuming that there are n terms per unit length, n terms per unit length. So in our case, the length now is H. So if the length is H, right, then how many turns? By unitary method, you will have NH turns, isn't it? So you will have NH turns for the length L. And therefore, our BL is equal to mu naught I becomes BH. This becomes BH. Okay? BH, and that's equal to mu naught I, okay, NH. Okay? So therefore B is equal to mu naught. Now the extra thing is N into I. In the previous case, now if you say N equal to 1, right, then B equals to mu naught I. What happened to my 2 pi r and all? Because that was a circular thing, right? This is only, this is a rectangular thing. That's how you get. So the direction of the field is given by the right hand rule. The solenoid is commonly used to obtain a uniform magnetic field. That's about the solenoid. Okay? So the explanation is important. You won't need any of this derivation for the exam point of view. Okay? So the next topic is the toroid. So, if I do that winding of that, like circularly, like that it is, for example, then this kind of a thing is called a toroid. So, obviously, when I am sending this, I can't just close like that, right? I can't be closing. Somewhere I have to open and then send the current, isn't it? So let's suppose I have like that. And we are assuming like that we are sending a current. So basically the current would be going from some direction. Earlier one was like a straight line. Now this is a circular thing. So where is this toroid? Toroid is a hollow circular ring on which a large number of turns of the wire are closely wound. Now look at the previous one. There, we have not wound anything on a rod, isn't it? A long wire wound in the form of a helix. In this case, you have a hollow ring. On this ring we are winding. So there is a ring, and the ring has the winding around. That's what is the toroid. So it is nothing but a solenoid which has been bent into a circular shape to close on itself. See? So we can say the current is going now, same thing, outside this entire ring, you got a point Q. There is a point Q is somewhere here, and there is a point P here. So we assume that outside Q, it is very, very big, or it is 0. So the field B inside the toroid is constant in magnitude for the ideal toroid. Of course, it will be varying very, very small variation at different points in case of a non-ideal toroid. Now look at picture 419b, second picture. He is assuming similarly all the entry of the the current and exit of the current. Okay, it is only the representation, the picture is important, nothing else is important here. Straight away see the second part, L is equal to, he has put the 3 circles. You see in that 1, 2 and 3. Similar to the Gaussian surfaces, right? Here he is having 3 loops, ampere loops. Okay? So 3 circular ampere loops, 1, 2 and 3 are shown by the dashed line. Okay? So 1, 2 and 3 are shown by the dashed line. By symmetry, the magnetic field should be tangential to each of them and constant in magnitude for a given loop. So the circular area is bounded by loops 2 and 3. It is loop 2 and 3, right? So circular area loop 2 cuts the toroid so that each turn of current carrying wire is cut once by loop 2 and twice by loop 3. So the magnetic field along the loop 1, let that be V1 in magnitude. Then using the ampere circuit law, L is equal to 2 pi R1. R1 is the radius of the innermost imaginary loop. Therefore, substituting into the top one, V1 into 2 pi R1 equal to mu naught into 0. Why 0? Inside there is no current, no? Because that is not part of the wire. That's why V1 equal to 0. Thus the magnetic field at any point P in the open space inside the toroid is 0. So we know here B is 0. Here he obtained B is 0, and he gives a reason why. He says V1 into 2 pi R1 equal to mu naught into the current enclosed I. This I is equal to 0. No current is enclosed. Okay. So what he is trying to do, you have a circular ring. He assumes 1 ampere loop here, another ampere loop here inside, and third ampere loop here. This is the third one, this is the second one, this is the first one. He applied for the first ampere loop. There is no current because of empty space, that's why it became 0. Clear, right? Now, thus the magnetic field at any point in the open space inside the toroid is 0. Let us see now that the magnetic field at Q is likewise 0. Magnetic field along the loop 3, let the loop 3 be D3. Once again from ampere circuit law, you got 2 pi R3. Okay. However, from the sectional cut, we see that the current coming out of the plane of the paper is cancelled exactly the current going into it, thus IE is 0 and therefore D3 is also 0. Now only for second ampere loop. That second ampere loop is similar to what we have done. Therefore, we get B into 2 pi R equal to mu naught Ni. So for the loop, second loop, B naught into 2 pi, whatever is the radius you want to put there, that's R equal to mu naught, it's an empty space, n into I. N is the number of turns you require. Okay? And therefore B is equal to, we will make B as a subject, or B as B naught. So B for a toroid is equal to mu naught n I divided by 2 pi R. So what is the result in for the result? We just say that n is equal to 2 pi R into n, average perimeter of the toroid, or the number of turns per unit length. So you get the same thing of mu naught n into I if that is equal to 2 pi R. In ideal toroid, the coils are circular. In reality, the turns of the toroid coil form helix, and there is always a small magnetic field external to the toroid. We consider that is a weak field, so we said it is 0. That completes the toroid part. So now we have, as I said, the next part is important. Many times the questions have come. Okay. This is a force between two, see, all these are important, parallel current carrying conductors. Two parallel, of course, infinite line, okay, parallel infinite line current carrying conductors. So they can say in a simple word, just parallel current. They may also say parallel current. Here we need to understand parallel current means obviously there is one wire and there is another wire. So there is another wire. I think at the class straight. There is one wire, another wire. These are the two parallel. Whenever you look at this parallel, right, we are looking at the current. Okay? One second, I'll just do that. So the current, both currents can be in the same direction, I1 and I2, or they can be in a different direction. One can be this way, that can be this way. So it can be this also. And there is a third one also. There could be I1 and I2 may be same, magnitudes may be same. So these are all the things we'll be considering, and then we'll be getting an expression. Based on, we know that there is a magnetic field. Why we are talking about force here? If there is a magnetic field, then there will be a magnetic force. Got it, right? So the field will definitely generate the force between these two conductors. So look at the picture. She does give one picture and it says IA and IB, two conductors A and B. So what is saying? Two long parallel conductors A and B separated by a distance B. Read from second paragraph. Okay? Carrying parallel currents IA and IB. The conductor A produces, that's the underline, need to. The same magnetic field BA at all points along the conductor B. Understood that, right? So you have So we consider first IA. IA is going in this direction. This IA, because this is using your right hand thumb rule or whatever, you have so many points on conductor B. At all these points, whatever is the magnetic field created is same. So that is, let's call that as dA, because it is due to the current going in A. The right hand rule tells us that the direction of this field is downward. The direction of that field will be like this. This is dA. So that means you will have something going like that along that downward. Okay, now consider the other part. So we need to get the expression for dA. dA is equal to, if we are considering the distance to be d, we consider the distance between them is a d. So that means that a distance d. So b is equal to, you have mu naught Ia divided by 2 pi d, because it becomes the radius, isn't it? So here also and parallel another conductor also. So this is what your radius. Clear, right? So the next one, the conductor B carrying current IB will experience sideways force due to this field dA. So because of that, the conductor B will move little bit. The direction of this force is towards the conductor A. So because this dA is there, it will be, this wire will be pulled towards that. Understood, right? It's kind of attracted towards the IA. Let us label this force. It is called B due to the current A. Okay, let's label this FBA. Okay. So now the magnitude of the force is given, right? We have the field B. We remember that F is equal to DL or BIL. We did that, right? The force. So in this case, the force that FBA is equal to whatever is the B, that means the BA, this is the one which is causing, and the current that is going is IA, and what is that length? Is the total length. This current is IB. Okay. So the force on the segment L of B due to A. So we are considering only one part of this segment, for example, this part of the length. Yes, and therefore you got BA multiplied by length, and this current is nothing but IB. Of IA, and because the current has to be going through that only. That's how we learned. Okay, so IB, BA, IB into L. So now I have to substitute for BA. This is nothing but the BA. So I substitute that. You got mu naught IA, IB into L divided by 2 pi d. Clear?
Yes, sir.
So if you do the similar thing now, reverse it actually. That means, let's suppose we have FAB spanning out. So FAB will be exactly equal to FBA, and that will be directed towards B. Okay? Because the current direction is like this. So what we will have is B. That means the force on A due to IB. That's the one. It will be same, but it will be opposite direction. Opposite direction meaning it will be this way. So the first conductor is pulled towards the second one is pulled towards the first. That is what is the one mark question they will ask. Whether they will be, the forces will be pulling them towards each other or pushing them away, attractive or repulsive force. Got it? So the parallel currents attract. So these parallel currents, if both are IA and IB are in the same direction, then they will attract each other.
Yes, sir.
So knowingly, when they are actually putting on electrical engineering on the top of the towers, right? Exactly the same scenario. So there has to be some distance between those two conductors. If the current is in the same direction, same phase, same everything, there will be some minimum distance. Okay. Otherwise, they attract with each other and you get a spark. Okay. Next part is anti-parallel current vector. So what do you mean by anti-parallel current? If IA is one side and IB is the other side, this is called anti-parallel. So anti-parallel current is vector. That's all this question, and in both the cases, the magnitude of the force, if you are talking per unit length, then you have to divide by L, and that is what the expression 4.25. The magnitude of this force between the two current carrying parallel conductors is given by mu naught into IA into IB divided by 2 IB. Got it? It is used to define ampere, which is one of the 7 applied by units. Okay? So look at the last line. When a steady current 1 ampere is set up in a conductor, the quantity of charge that flows through its cross section in 1 second is 1 coulomb. That's how we define the ampere. Right? In the very beginning, when we talked about the charges, total charge and charge. Okay? So that sums up the parallel conductor. The next point is torque on a current loop on the magnetic dipole. For example, we keep this kind of a loop in a magnetic field, and then what will happen? Okay, so that is what the next topic. Let me see how much time. Okay, so we have much time here. So why we talking about the torque after the force? We talked about force, and that's basically a magnetic force. And that magnetic force created attraction or kind of a repulsion that we talked about already. The next one we are talking about is a torque on a coil which is carrying current carrying. Placed in a magnetic field. So let's suppose you have a huge force like that. You have studied this probably in a 10th standard, okay? And this is kind of a north pole, and you have kind of a south pole like that. Alright, and then you make sure that there is a coil. I think this is pretty bad. Let me try it. Actually, how it looks is and then on the back you have, for example, and if the current is going to this. This is what in reality what we'll be talking about, okay? And because of this particular, the force will be 4 times will be going from north to south like this, right? Magnetic force. Something will happen to this. It will be, if you are connected this on something, it will be made to move. that is nothing but a surface force. That's what they call about a torque. So in a simplified picture, what they have done is, if you see in the book, having a rectangular coil and they have kept that between these magnets, north and south. Okay. So this is obviously the current carrying and magnetic field will be like that. Okay. So look at the picture, what is given in the question. So you see there is a north pole and it has got the width or something is given as a B. A rectangular loop carrying a steady current I placed in a uniform magnetic field experiences a torque. So torque meaning the left side thing will go up, right side thing will come down, or the other way around, depending on the direction of the current as well as the magnetic field. So this is analogous to the electrical dipole. Anyway, consider the simple case in the rectangular loop is placed in such that the uniform magnetic field is in the plane of the loop. What does it mean? The uniform magnetic field B is in the plane of the loop. This is called plane of the loop. Let's suppose this plane in this case is the horizontal. The loop is horizontal. Okay. And you got a magnetic field going parallel to the loop. So that is the first case. This is present figure 421A. It is parallel, almost same. The field exerts no force on AB and BC. Why? Because A, B, C, D. See this AD and BC, they are parallel to B, magnetic field B. Right. Therefore, there won't be any cutting effort. Okay. So, it is perpendicular to on the edge of the loop and exerts the force F1 on it, which is directed into the plane of the loop, and its magnitude F1 is equal to I into B into B. If you look at the picture, okay, B is nothing but the length of the magnet, okay, and capital B is the magnetic field, I is the current going here. So we are still using the BI value. Okay. Why B is taken? Whenever they say this is B, this is also B. Understood, right? In the previous case, when we have done that, whatever is this dots and all the stuff, we assume that this is plane B, C, D, like this. And finally, we said this is what is that H or whatever. Remember? So this H is what we are using. There also you use H. So that's how you will get the magnetic field multiplied by the current going through, multiplied by the D. Okay? So this is equal to the force F1. So similarly, exert the force F2 on the arm C. So you have both on AB and C. So the F2 also will be same. So the net force on that is 0 because current is going in the opposite direction in AB and C. So the net force on the loop is 0. But then there is a torque on the loop due to the pair of this force F1 and F2. Okay. So they are opposite, but then they are opposite coupled. That's why we get the picture B. 4.21 B. F1 acts in one direction, F2 acts in the other direction. Okay? So they form a couple, and that's how you will get the rotation. Okay? So view of the loop from AB, and it shows that the torque on the loop tends to rotate it anti-clockwise. This torque in the magnitude tau is given by whatever is the force multiplied by the perpendicular distance. So that picture I am drawing for that. If you are assuming that this is the center of. So we got this point, and we have F2 this direction, and F1 will be another direction here. They are opposite, but then they are at a distance of a by 2, because we consider the distance between this and this is a, and therefore total torque, which is anti-clockwise, equal to F1 multiplied by a by 2 plus F2 multiplied by a by 2. So you get totally, you can't just add them until unless F1 and F2 are equal, then you can consider that. If they are equal, then you can substitute whatever you got. You got IB, B, right? Material is BIB. So that's equal to BI small b a by 2 plus BI B a by 2. So this gives totally the tau equals BI AB. AB is nothing but, if this is B, this is A. This is the area of that rectangle. Okay? So that's what is called the. So if you say A, area of the rectangle is what it is. What happens is now, because of this aspect, obviously the position of CD and AB will be changed. So in the next case, what happens is, so instead of this, now it's anti-clockwise, right? So this thing like that. Okay? This is moved. Okay, this is moved down. This is moved up and this is moved down. One second, I'm getting it. నేను బాగున్నారా ఒక 10 కాల్ చేస్తాను మెసేజ్ sorry back. So now if you look at the picture 422A, it goes with a little angle. Okay, so that picture has to be drawn exactly the way that angle occurs. Okay, so now it makes an angle theta. So that theta, you look at the B part, 4.22 B. Okay, so 4.22 B if you look at it, and that is sufficient if you draw 4.22 B, not 4.22 A, and directly go to the last part, 4.27, equation 4.27. Tau is equal to F1 A by 2 into sin theta. So if I draw that, actually as I said, you have now, earlier this was like that. So now this is the theta. So you will have like this and like this. So F2 and this is F1. Okay. This is theta, then this is 90 minus theta. And therefore the expression comes simply tau is equal to F1. Okay. You got the same thing. I B by 2 sin theta will come extra. Similarly, for that B I B A by 2 sin theta. So now totally I A B sin theta. This A B is nothing but area. B I A, area of the rectangular lake sin theta. Area of the. So why we say this area of loop? We just give area of loop and ask you to find out the arc. You just substitute in that as a 1 mark question and it gets that. Okay, IAB sin theta or IBA BIA sin theta. Clear?
Sure.
So if you want to talk about now the dipole stuff, because this topic itself was torque as well as a dipole. So magnetic moment of the current loop, this is nothing but the current loop, and we defined, there we had a dipole moment P is equal to something, remember there P is equal to some expression was given as we studied. Here we have a magnetic moment M is equal to M is equal to whatever is I multiplied by A. So this is nothing but the area vector we call it as A. So if I want to actually, if there is an angle theta, then we have tau is nothing but tau is equal to the magnetic moment cross product with tau is this magnetic. We are actually trying to express this tau in terms of this magnetic moment. What is that I am doing? Actually doing replacing this IA with the M. So I am replacing that B into M into sin theta. From the vector algebra or vector theory, if you have two M, okay, M is having the area vector, this area vector. Okay? So when the sin theta comes, it's nothing but you are having a cross product of M, because M contains a vector and B contains a vector. So tau is defined now as a cross product of magnetic moment, cross product of the magnetic moment as well as the magnetic field intensity. So he compares that and says it is very similar to P into E in the electrostatic water. Here, the small rotation of the coil produces a torque which brings it back to its original position. So it keeps on moving like that and comes back to original position. So when they are anti-parallel, the equilibrium becomes stable as any rotation produces a torque which increases with the amount of rotation. So if the loop has n closely wound turns, instead of IA, it becomes, if this is for 1 turn. If you have n turns, this becomes n times I A. Okay? So that's the only thing. Otherwise, it's the same thing. Why n turns? Why n turns? We are talking about n turns because in the beginning, here, as I said, the picture, top picture. In fact, this is how it will be. Meaning, rectangular or circular things are wound on a core. So that is how the n number of turns are there, and n comes into the picture. Okay. So we completed a good thing for before we go for the current circular current loop as a magnetic dipole. That's what we will talk in the next class. Okay. We don't cover that now because that immediately takes us to the moving coil galvanometer. Again, important question. Okay. That's why I don't want to cover the next one in rush. Okay. That's a circular current loop as a magnetic dipole. Okay. That will be talking in the next class. Okay. Now coming back to where we started. So we started where we left the other day. Our law gave the expression for magnetic field intensity or magnetic field density at a distance of x from the center of the loop. That is what on the top we got B is equal to dSi or mu naught I r square divided by 2z square plus r square to the power of 3 by 2. That's where we started, and we said the direction of B is given by the right hand thumb rule. If you look at how these four fingers are curling or around, okay, current carrying conductor, the magnetic field will be along the finger if the current is along the thumb. If the field is along the thumb, then the current will be along the finger. That is what the direction for the magnetic field applying the right hand thumb rule. Okay. Then we brought in the Ampere's circuit law. This is another way of getting the expression. I am stressing that this is another way to get this expression, not only from the torque law, we are using Ampere's circuit law. Assuming that you have a surface, and from that surface you are having a circular part, the closed circular part, and through that we are assuming there is a magnetic field on the periphery. So then, using this expression, line integral is the one when we go from start to end. That's what it's called, line integral. Line integral B dot dl is equal to mu naught I. This is the Ampere's circuit law. So we found out observations from that, and then we said if we change the direction of the current, then the magnetic field also, the direction will be changed. Okay? But if you throw the iron filings, they will be distributed like this. And in this particular expression, we got that B is equal to mu naught I by 2 pi r, exactly same as what we got from the torque law. By using that, line integral of dl is nothing but a 2 pi r. So then we went with the solenoid. Okay, solenoid, we consider one loop, that was the one turn. When we have many turns, and then internally if you use the air as a medium, you will have a magnetic field going through the center like that and distributed along this curve what we have drawn. So solenoid is nothing but having many turns of a coil and turns of a coil. So in order to get an expression at a different point outside this coil, inside as well as on that one. So we assume that this is how the wire is wound. I have considered the rectangular Ampere loop A, B, C, D, and for the AB part only we are able to get, because the BC they are perpendicular and C are perpendicular, there is no big cancel with each other, whatever is the field coming through. This point is outside, CD is therefore nothing is there. Only for C we have found out how much is that value. So we got that value saying that D is equal to mu naught Ni. This NH, HH gets cancelled. Okay. So why NH? Because of the tangent per total length of H. And therefore we got D is equal to mu naught I. Then we move on to toroid. Toroid is nothing but a solenoid and put that in such a way, solenoid on a circular, either ring or some metal ring or some conductor ring. So not as a conductor, it's insulator ring. So toroid is what we try to get, considering the internal part of it, that means the hollow part of it, or inside of it, and then in the ring, and then outside the ring. So out of all the things, for the 3 it is 0, for the 1 it is 0, for the 2, that means the second part, that means inside the ring, hollow part of it, then you will see the magnetic field inside that is mu naught Ni divided by 2 pi r. So then we consider current parallel conductors, two parallel conductors. How much is the force, FAB and FBA? F is due to the current going in the other conductor. So this is the parallel case and the one is the anti-parallel case. Okay? So in the both are parallel, in the direction is same, they attract. In the other case, same, they attract. Okay? Then we went with one such a loop kept in a uniform magnetic field. So for that magnetic field, equal and opposite direction. If it is equal, then we got BIA by 2 is B, so it is totally BIA AB.
But these are will push in the anti-opposite direction, we have a picture. It will continue to move around. Okay? So, what the concept of magnetic moment is defined that as IEA. A is the area part of it, and we substituted this one, okay, IA, and this is M, then we got B sin
theta, and therefore we finally know tau is nothing but cross product of M and V. Done? Okay, so the next class one is the important one. Okay, that's next class question is guaranteed. Like moving class galvanometer, many times it has come. Okay, so Monday. Right. Okay. No problem. Bye. Stopping the share and in the call.